in the figure, find the magnetic field in terms of mu naught, the permeability of vacuum, at point A for the current carrying loop, okay, consisting of radial lines and segment circles whose centers are at point A, and then they give us some values, and they tell us the current is 12 amps, which is good. All right, so first thing we're going to do is there's two formulas we need to think of here. So we have magnetic field due to a loop, which is mu naught, that's a terrible mu, mu naught I over 2R. In the similar magnetic field formula we're going to want to know is due to a line, which is mu naught I over 2 pi R. And these just, you memorize them. You can drive them, not worth it. There's kind of standard and taken for granted. So I'm going to label these segments right here. We're going to call this 1, 2, 3, and 4. And then these segments, since we have current going this way on that one, current going that way on the bottom one, they're basically just going to run anti-parallel to each other, opposite directions, and they'll cancel each other out. So I'm not going to worry about this section over here. And so a loop like this with a current going that way, it's going to create a magnetic field. If we have a current going in a circle, it's going to create a magnetic field in the center that's going straight. And so the rule used for this, the right-hand rule, is you wrap your fingers in the direction of the current, and your thumb will point in the direction of magnetic field. So we have current going this way, the magnetic field is going to be going out of the board. And for a straight wire with current going, let's say this way, you place your thumb along the direction of current and wrap your fingers. And for this, the magnetic field is going to be going like this, where at this point the magnetic field is coming out of the board, and this point the magnetic field is going into the board. So that's the basic idea between current carrying wires and loops. So for this then, we have basically 2 wires and 2 loops. The wires are going to create magnetic fields. So this current's going this way, current's going that way. This is going to create a magnetic field going like that. That's terribly drawn, but that's okay, because it's going to create a magnetic field around the wire, and since this wire is in line with point A, it's not going to have any effect on it. Therefore, we can ignore 2 and 4. So if we look at this here, the total magnetic field is going to be magnetic field due to 1, plus magnetic field due to 2, plus magnetic field due to 3, plus magnetic field due to 4. These should all be vectors. And since these 2 lines here are in line with A, and they're lines, they're going to have no effect. Because a line is going to create a magnetic field around the wire, not at a central point that's in line with the wire. So 2 and 4, zeros. Now we have left just 1 and 3. So B1 is a loop. That's going to be mu naught I over 2R, where R is this radius here. In fact, it's going to be, I'm going to call this R1. And it's not a complete circle. It is only 72 degrees of a full circle. So what we're going to do is we're just going to ratio this by the portion of its complete circle. So we're just going to say 72 degrees out of 360. And I'm just going to use I here because the I through the loop section 1 and I through the section 3 are the same. It's all the same current. It's all in series. So then I'm going to do B3, which is going to be mu naught I, and again 72 over 360. And I'll put all degree symbols here, but as a unit, but it doesn't matter because they're going to cancel. All over 2R3. And R3 then is going to be 3 centimeters. And I'm going to do a little negative symbol right here. And that's because if you do the right-hand rule for 1 up top, B1 is going to be into the board. You can do the right-hand rule for B3, this curved section right here, is going to be out of the board. And so I'm just, for convenience here, going to say that positive is along B1, which is into the board. Always remember that positive is the same as B1. All right, so B total is going to equal, so we're going to have mu naught I over 2 times 72 over 360 times 1 over R1 minus 1 over R3. And I'm going to convert these over to meters as well. So I'm going to do some simplifying real quick, put some values in here. So mu is 4 pi times 10 to the negative 7th. We have I, which is 12. We have 72, which is 72. We have 2, which is 2, and 360, which is 360. R1 is 0.06. 1 over 0.06 minus 1 over 0.03. Yep, now we're going to do some simplifying. So let's see here. 2 and 72 becomes 36. 36 and 360 becomes 10. 4 and 12 become 48. And 48 times 3 is like 150. So 150 divided by 10 is 15. So we have 15 times 1 over 0.06, which I'm not going to try and do in my head. If I was a better person, I would, but I'm not going to. And this is times 10 to the negative 7th. All right, so I'm going to go to Wolfram to solve this part. So we have 1 divided by 0.06 minus 1 divided by 0.03. And that gives us 16.6 equals 15 times 16.6 times 10 to the negative 7th multiplied by 16.6 times 15 times 10 to the negative 7th. I'll leave off the 10 to the negative 7th for now. So we have 250. So we have 250 times 10 to the negative 7th. This is going to be in Teslas. And it's negative, which really means it's going to be in the direction of B3. So I'm just going to say out of the board. Because the negative and positive, that just gives you direction. So 25. Oh, they did it solved in terms of mu naught. Okay. So let's see, 250 times 10 to the negative 7th times mu naught over 4 pi times 10 to the negative 7th. 4 pi is 12, which is the same as 25. So we have, scroll down a little bit. So this becomes 10, that cancels, and we have 10 mu naught. That's just a mu naught right there. So the value here is going to be 10 mu naught. So the answer for this one, I would say, is 10 mu naught. So key idea here is you have two equations. One for a magnetic field loop, one for a magnetic field due to a line. There's two right-hand rules. For a loop, you wrap your fingers along the direction of the loop, and that gives you a magnetic field. For a line, you lay your finger along the line in the direction of current, and your fingers, which will give you a circle, will give you the direction of the magnetic field. Since the lines are in line with the point, they have no effect. You look at just the loop, and then to find out how much effect you have from the loop, you ratio the angle of the loop over a complete circle. And then you do some math, and you get an answer of 10 mu naught. So, hope that helped. See you next time.